Well, we finally know why the world's largest supercomputer landed in Memphis. XAI founder Elon Musk says it's simply because the old Electrolux building was empty, in good shape, and large enough to house the operation.
For years, the giants of the auto world were certain they had finally cornered Tesla. The hype was cooling, the Cybertruck was stalling, and the oldest rule in the business still held firm. A car could be fast, or it could be cheap and efficient, but never both at once.
Then Tesla quietly revealed the one thing almost nobody believed it could build. A piece of hardware so far ahead that rivals may need a full decade just to copy it. It does not look like a revolution. It looks like an ordinary part. And it may have already ended the race. There are just so many false dawns with self-driving, where you think you got the problem, have a handle on the problem, and then turns out you just hit a ceiling. The forgotten story. For more than a decade, the world's biggest car makers fought a battle many believed would decide the future of transportation. Electric vehicles did not just add a new kind of car to the lineup. They redirected the entire global auto industry. And one company kept appearing at the front of that race. Tesla. In the beginning, almost no one expected it to stay there. Next to Ford, General Motors, Toyota, and Volkswagen, Tesla looked small and inexperienced. Those legacy companies had spent generations building enormous factories, refining precision engineering and stitching together worldwide supply networks. The smart money said it was only a matter of time before they caught up and pushed the upstart aside. For a while that looked likely. I mean, this is really an amazing work of engineering. There's just never been an electric motor like this. I mean, you could pick this motor up with your hands and it can accelerate a 2-ton car to 60 miles per hour in 2 seconds. The competition genuinely improved. Rival electric cars became more stylish, more reliable, and more practical for daily driving. And battery performance climbed faster than many had predicted. Analysts pointed to the obvious math. The legacy giants sold tens of millions of cars a year, dwarfing Tesla's output, and could absorb electric losses that would have sunk a smaller firm. Some began forecasting that Tesla's advantage would eventually vanish entirely. The legacy makers were not standing still. General Motors had built electric cars decades earlier and was pouring resources into a new battery platform. Volkswagen had pledged tens of billions toward an electric lineup in the wake of its diesel scandal. And nearly every major brand announced a wave of battery-powered models. On paper, the resources arrayed against Tesla looked overwhelming. The widespread assumption was that once these giants turned their full manufacturing might toward electric cars, scale alone would settle the contest. Then in June 2021, at the Model S Plaid delivery event, Tesla showed the part that changed the conversation. It was not a new battery or a software update. It was a motor built around a rotor wrapped in carbon fiber. Veteran Tier-1 engineer Sandy Munro, whose firm Munro and Associates strips competitors' vehicles down to the bolt and costs out every component, kept returning to that single detail when his team cut a Plaid drive unit open. The dangers would be that artificial general intelligence or digital superintelligence decouples from a collective human will and goes in a direction that for some reason we don't like, of whatever direction it might go. The carbon sleeve was the reason the motor could do what rivals could not, and it hinted that Tesla had stopped competing on the same terms as everyone else. That moment quietly inverted the underdog story. The legacy makers still held the advantages everyone had counted. The factories, the dealer networks, the century of brand trust. But the thing they could not buy off a shelf was the manufacturing know-how baked into a single spinning part. The race the analysts had been scoring on volume was about to be rescued on engineering. And Tesla had a head start no balance sheet could close. Volume could be bought with capital and time. The specific craft of making a punishing part cheaply and reliably could not. And that was the ground on which the next phase of the contest would be fought. The pressure inside. By late 2025, the company that built its name on inevitability looked vulnerable. The Cybertruck sold to the world as the future of transportation had become a problem. Sales landed far below what Tesla had projected, and the truck turned into one of the most talked about disappointments in the company's history. The registration data made the situation plain. According to S&P Global Mobility, of the 7,071 Cybertrucks registered in one quarter, 1,279 went to SpaceX, and roughly 60 more went to other Musk-connected entities. Put another way, nearly 1 out of every 5 Cybertrucks registered during a single quarter went to companies connected to Musk himself, including SpaceX and the artificial intelligence venture XAI. Internal registrations were helping prop up the figures. Recalls were chipping away at confidence, and buyers suddenly had a dozen electric options to choose from. That mattered because Tesla's reputation rested on a single claim that anything it touched reshaped the category around it. The Cybertruck was supposed to be proof. Instead, it became a reminder that even Tesla can swing and miss, and Musk knew it. He needed something fundamental. The kind of advance that changes what is possible rather than what is fashionable. The timing made the need sharper. The early electric market had rewarded novelty, and for years simply being electric was enough to draw buyers and headlines. By 2025, that advantage had evaporated with cheaper rivals flooding showrooms and incentives shifting underfoot. In a crowded field, a striking shape and a famous name no longer guaranteed sales. And Tesla's answer could not be another design statement. The Cybertruck's troubles ran deeper than slow sales. The truck was hit by repeated recalls, including issues with exterior trim. And talking about some of the sort of details behind it. So, we have an all-new battery pack. And then something we're really proud of is the new carbon-sleeved rotors for the motor that could detach and with the accelerator pedal. Each one reinforcing the impression that the most futuristic product on the road was also among the least finished. Production that had been promised in the hundreds of thousands per year ran at a small fraction of that. For a company whose valuation rested on the belief that its next product would always redraw the map, a flagship that under-delivered was more than a sales miss. It was a crack in the story. The company had the appetite for it. Tesla pushed its capital spending past $25 billion, pouring money into artificial intelligence, robotics, and custom chips at a scale most car makers reserve for an entire decade of factory upgrades. Much of that budget flowed into things a traditional automaker would not recognize as car making at all. Training computers, in-house silicon, and the early stages of a humanoid robot program. While its competitors treated those areas as side projects, Tesla treated them as the main event. And the open question was where the next undeniable advance would actually come from. Tesla's history with raw materials offered a clue. When Musk introduced the Cybertruck's body, he described an ultra-hard cold-rolled stainless steel alloy that Tesla had developed in-house destined for both the truck and the Starship rocket. Tesla builds its materials rather than buying them, then spreads the result across rockets and cars alike. The same instinct was already at work inside a drive unit program aimed not at speed, but at cost. If untangling the technology quietly reshaping the future is worth an hour, subscribe and turn on notifications because the next breakdown lands the moment it is ready. Now back to the engineering because the reason it unsettles the rest of the industry sits in the physics. Breaking the rule. For years, the industry treated one compromise as a law of nature. An electric car could be blisteringly fast and powerful, or it could be efficient and travel a long way on a single charge. But not both at once. Higher performance made cars heavy, prone to overheating and dependent on massive cooling systems just to survive a hard run. Building for efficiency made them tame, missing the acceleration that defined the brand. Most companies decided physics had drawn the line and spent their effort optimizing around the edges. Tesla's carbon-sleeved rotor, the heart of the 2021 Plaid motor, attacked the line directly. Inside every electric motor sits a spinning rotor, and as its speed climbs, centrifugal force tries to tear it apart from the inside. Traditional rotors warp, fly apart, or cook themselves into scrap at high speed, which is why most passenger motors are held to far lower revolutions. Wrapping the rotor in carbon fiber, a material both extremely strong and extremely light, held it together under that stress. It is the same family of material trusted in aerospace and motorsport. Applied to one of the most punishing jobs in the car, the type of motor made the problem harder. Many efficient electric cars use permanent magnet motors in which magnets fixed to the rotor pull it around. But those magnets depend on rare earth materials and lose strength as they heat. High-performance units drive enormous current through the rotor at extreme speed. And the faster the rotor turns, the more violently it tries to fling itself apart. The carbon sleeve let Tesla run the rotor far harder than a bare metal rotor could survive, which is precisely what unlocked both the speed and the efficiency at once. The result was a drive unit that can spin at more than 20,000 revolutions per minute, a level almost never seen in a passenger vehicle. The idea behind Neuralink is to try to more tightly couple a collective human world to digital superintelligence. Raw speed was not the real breakthrough. The control and stability the carbon wrap held at those speeds sharpened. The motor's magnetic performance, letting more electrical energy turn into motion instead of bleeding away as heat. More of the battery moved the car, and less of it was wasted as the noise, friction, and warmth that quietly drain range in ordinary motors. That efficiency cascaded into the rest of the design. A motor that wastes less energy runs cooler. And a cooler motor needs less of the heavy plumbing rivals bolt-on to survive. Fewer pumps, smaller radiators, shorter coolant lines. Stripping that hardware out cut weight, freed space for batteries or cargo, and removed failure points. So the same battery pack delivered more range. A single change at the center of the motor rippled outward through the whole vehicle. Spinning faster also let the motor be smaller. A motor's power depends on both torque and speed. So a unit that can safely turn at very high revolutions produces the same power from less mass and metal, then uses a fixed gear reduction to deliver it to the wheels. That is why a drive unit one person can lift can move a heavy sedan with the force of an engine many times its size. Compactness in turn freed space and cut material cost, looping back into the same advantage. The Model S Plaid showed the full effect. It uses 3 electric motors to produce more than 0.00 horsepower, and it launches from 0 to 60 miles per hour in under 2 seconds. A figure that once belonged only to race cars and exotics worth many times the price. Underneath the violence, it remained a comfortable luxury sedan, capable of carrying a family hundreds of miles on a charge. Speed, efficiency, and everyday usability arrived in one package, breaking the rule the industry had accepted as permanent. The design also made copying it dangerous, and the difficulty lives on the factory floor. The carbon fiber arrives as a delicate pre-impregnated tape, and it has to be wound around the rotor under exact, unwavering tension, then cured under heat and pressure until it sets into a single rigid shell. Wind it too loose and the rotor flexes and fails at speed. Wind it too tight and the fibers crack. Miss the temperature or the timing during curing and the whole part becomes scrap. Every finished rotor then has to be balanced to a tolerance most factories never confront, because a wobble invisible at highway speed becomes a violent self-destructing vibration at 20,000 revolutions. A rival cannot photograph the part and reproduce it. Well, they're all very difficult technology challenges. But the overall goal of my company is to maximize the future of civilization. Like basically maximize the probability that civilization has a great future. The process has to be rebuilt line by line and failure by failure, eating the cost of every ruined rotor along the way. Carbon fiber rotor sleeves do exist elsewhere, supplied by aerospace and motorsport specialists. So the idea itself is not a secret. The mode is doing it perfectly thousands of times at mass market scale and acceptable cost. And some analysts suggest matching that could take rivals close to a decade. That distinction between knowing the idea and producing it cheaply is the quiet center of the whole story. A rival can read the same papers, buy the same carbon fiber, and even build a working prototype, and still lose money on every unit it ships because its scrap rate stays too high. Tesla spent the painful years learning to keep that scrap rate low. And the low scrap rate is not a patent or a press release. It is institutional memory built one ruined rotor at a time, and it does not transfer. This is the lens through which tear-down specialists, like Monroe and Associates, read apart. Their work is not to admire the engineering, but to estimate down to the dollar what each component costs to manufacture. And a design that performs brilliantly while bleeding money in production earns no praise from them. When a firm built to find waste concludes that a part is both better and cheaper than the competition's, it is describing the rarest combination in the business. For decades, the industry had insisted that drivers must choose between speed and efficiency. And the carbon-sleeved rotor stood as proof that the choice was false. But demonstrating that something is possible and making it affordable enough to sell by the million are very different problems. And the second one is where Tesla turned its attention next. The motor showed what the company could engineer when it refused to accept a limit. The harder question, the one that would decide whether any of it reached a wider market, was whether a part this demanding could be produced at a price ordinary buyers could actually reach. Why rivals stall? Plenty of companies can build a jaw-dropping prototype. Building millions of cars consistently at prices ordinary people can afford while still turning a profit is an entirely separate sport, and it is where most companies fail. The auto world is littered with the wreckage of firms that promised to change transportation and collapse the moment real production began. Tesla learned that lesson the hard way through years of manufacturing wars, production lines that refused to work, robots that had to be torn out and replaced by hand, and stretches when the company sat weeks away from running out of cash. Those years now show up in the next chapter. At its 2023 Investor Day, Tesla laid out a next-generation drive unit engineered first for manufacturability, and it attached a number to the goal. Tesla wants the entire drive unit, the motor, the electronics, and the gearbox together to cost only around $1,000 to produce. Some competitors reportedly spend 3 to 5 times that just to reach similar performance across hundreds of thousands of vehicles a year. That gap becomes the kind of margin that funds entire new product lines while rivals fight to break even. On a single car, the difference of a few $1,000s looks modest. But multiplied across a million vehicles, it becomes billions of dollars of headroom that a competitor simply does not have. It also gives Tesla room to cut prices in a downturn and still make money where competitors lose it, turning a price war into a weapon rather than a threat. Tesla attached 2 more goals to that same event: to strip rare earth materials out of its motors and to cut the costly silicon carbide in its power electronics by roughly 75%. Both remain targets rather than shipped reality. And as of early 2026, there is no confirmed commercial rare earth-free Tesla drive unit on the road. The rare earth goal matters most. The magnets in most powerful electric motors rely on elements like neodymium and praseodymium, whose refining is dominated by a small handful of suppliers concentrated largely in one country. Ultimately, we can have a fully sustainable energy economy. And it's those three things: solar, wind, stationary, battery, electric vehicles. That concentration hands a single government real leverage over the cost and even the availability of motors built anywhere on Earth, with prices able to swing on a policy announcement. A motor that needs far less of that material steps partly outside that web of leverage. The push to cut silicon carbide follows the same logic, trimming dependence on a scarce, expensive semiconductor that manages the flow of power between battery and motor. Each substitution does double duty, lowering the bill of materials while removing one more outside supplier that could raise a price or slow a shipment. One by one, the choke points that still squeeze the rest of the industry are being engineered out of Tesla's cars. These advantages reinforce one another. Lower production costs lets Tesla lower prices. Lower prices pull in more buyers. More buyers raise volume. Higher volume buys manufacturing experience. And that experience cuts cost further. A rival trying to break into that loop has to do so from the outside, paying full price for every lesson while the target keeps moving, which is why catching Tesla on cost has proven so much harder than matching it on a spec sheet. Meanwhile, the competition was bleeding. Ford built genuinely impressive electric vehicles, the Mustang Mach and the F-150 Lightning. Yet its dedicated electric division lost billions of dollars a year by the company's own reporting. Enough that Ford delayed several planned models and leaned harder on hybrids. General Motors repeatedly pushed back the targets for its battery platform as its plants struggled to ramp. Volkswagen poured tens of billions into electrification, only to be slowed by software troubles inside its in-house unit. Lucid kept burning cash building beautiful cars in small numbers. And Rivian, despite genuine demand, lost money on roughly every vehicle it delivered while it fought to bring costs down. Among global rivals, only BYD competes at comparable scale, and it has overtaken Tesla as the top-selling electric vehicle maker. But it competes mainly on affordability, flooding markets with inexpensive models. Tesla is chasing something harder. The most advanced and desirable electric vehicles on Earth, made cheap enough to build at scale. Cheap is one target. Cheap, fast, efficient, and aspire-able at the same time is a target almost no one else is structured to reach. In order to do a carbon overlap rotor, you've got to wind it at extremely high tension. It's a very hard thing to do. We actually had to design the machine that makes the rotor. Rewriting the factory. The 1000-drive unit cannot be understood as a part in isolation because Tesla's deeper goal was to redesign the factory around it. At the same 2023 Investor Day, the company described what it called an unboxed assembly process, a break from the century-old method of building a car as a single body crawling down one long line. Instead, large sections of the vehicle would be built in parallel, painted and fitted separately, and joined together only near the end. Tesla projected that the approach could cut production costs substantially and shrink the factory footprint needed to build each car. The idea stays abstract until it is paired with how Tesla already casts its cars. Using some of the largest casting machines in the world, the company press forms the front and rear underbody as single pieces of aluminum, replacing dozens of stamped parts and the hundreds of welds that once joined them. Fewer parts mean fewer robots, less floor space, and fewer places for cost and error to hide. The structural battery pack then sits between those castings as a load-bearing element, so the cells help hold the car together rather than riding as dead weight inside it. Vertical integration runs underneath all of it. Tesla has pushed upstream into making its own battery cells, refining cathode and anode material, and even processing lithium at a plant in Texas, reaching for control over the raw inputs that competitors leave to outside suppliers. Each step it owns is a markup avoided, and a timeline it no longer has to wait on. The motor, the casting, the battery, and the assembly line are designed as one connected system, which is part of why the cost target reads as credible in Tesla's hands and merely aspirational in most others. This is the layer rivals find hardest to copy because it is not a single innovation that can be licensed or reverse engineered. It is the accumulated result of building cars badly, then less badly, then well, across more than a decade, with each lesson folded back into the next factory. A competitor can buy a giant casting machine, but it cannot buy the years of failed castings that taught Tesla how to use one. The breakthrough that changes everything was never a single engine. It was the machine that builds the machine, the hidden empire. Most people still think of Tesla as a car company. That assumption may be the most expensive mistake the auto industry has made because Tesla has fused several industries into one self-reinforcing machine with the drive unit at the center. Start with data. Every Tesla on the road gathers driving information. And that data trains the systems that power autonomy the way experience sharpens a human driver. More cars create more data. More data trains smarter systems. Smarter systems attract more buyers, and more buyers generate still more data. Tesla has stockpiled more real-world driving data than almost any rival. And a cheaper, easier-to-build motor puts more sensors on more roads to feed it. A competitor starting late does not just have less data. It would need years of cars already on the road, desirable enough that people actually buy them just to begin closing the gap. And those cars would have to earn their place in driveways on their own merits. Because no automaker can collect real-world miles from vehicles that never sell. The lead therefore compounds in a way money alone cannot shortcut. Each year Tesla stays ahead. It widens the very gap a rival would have to cross because the head start keeps generating the data, the volume, and the manufacturing practice that produced it in the first place. Then there is the battery. Tesla poured billions into its own 4,680 cells. Designed to raise energy density, cut cost, and simplify manufacturing because the battery is the single most expensive part of an electric car. Most competitors still buy their cells from outside suppliers and pay someone else's markup on the priciest component in the vehicle. Owning the cell lets Tesla design the battery and the car around each other from the first sketch. Tune the chemistry for the demands of its drive unit. Package the cells so they add structure to the car itself and change the recipe without waiting on a supplier's roadmap. The same independence runs through the software and the silicon. Tesla designs its own software, chips, and power electronics. And when global chip shortages froze most of the industry, it rewrote its software to run on whatever chips it could get while rivals idled their lines. It behaves less like a car maker than like a technology company that happens to build cars. The same control extends to driver assistance, where Tesla writes the software that interprets the road and runs it on a computer the company designed itself rather than assembling a system from a patchwork of outside parts. Its factories in Fremont, Shanghai, Berlin, and Austin form a fast-expanding industrial network, and planned sites in Mexico and potentially India could push costs lower while opening new markets. Each of them tooled to build a low-cost drive unit at scale. The supercharger network closed the loop. Critics once dismissed it as a perk for owners, but it became one of Tesla's strongest advantages because it was fast, reliable, and widespread. While rival networks struggled with broken equipment, failed payments, and dead screens. Eventually, the competition stopped fighting it. Companies like Ford and General Motors adopted Tesla's charging standard so their own customers could plug into Tesla's network. Tesla now earns revenue every time a rival's car draws power from one of its stalls, and it learns from the charging behavior of cars it never even sold, winning on the layer beneath the sale. There is also a second business hiding inside the first. Tesla builds large-scale energy storage from home batteries to utility-sized units that steady entire power grids. And that division has grown into a meaningful and relatively high-margin part of the company. The same cells, the same power electronics, and the same manufacturing discipline that go into the cars also go into the storage products, so progress in one feed the other. A company widely filed under automaker is in practice also one of the larger energy storage suppliers in the world. Where this heads, the closer the picture comes into focus, the harder Tesla is to call a car company. On the surface, it builds electric vehicles. Underneath, it is becoming a technology company built around energy, software, data, and artificial intelligence using cars as the way in. Compute is the clearest test of that shift. Tesla built its Dojo supercomputer specifically to train artificial intelligence on the flood of driving video collected from its cars tuned for exactly that work rather than borrowed from general-purpose machines. But the company wound down its dedicated Dojo program in 2025, redirecting that effort toward its custom AI chips and outside silicon from suppliers like NVIDIA. The supercomputer brand mattered less than the underlying bet that Tesla's future depends less on the cars it sells today than on the intelligence those cars can run tomorrow. Whether the training runs on a Tesla-built chip or a rented one, the scarce ingredient is the same. Billions of miles of video that only a large willing fleet can produce. And that fleet exists because the cars are cheap enough to build and good enough to want. That bet still rests on the data advantage. Most rivals rent their position, leasing computing power from outside providers and lacking the fleet that generates real-world driving data in the first place. Tesla builds the cars, gathers the data, and runs much of its own compute. Which is why solving self-driving and solving real-world artificial intelligence became the same problem for the company. Owning all three layers at once is something almost no other automaker is structured to do. The clearest expression of that bet is autonomy. In late 2024, Tesla unveiled a purpose-built Robotaxi, a two-seat car designed without a steering wheel or pedals and meant to operate with no driver at all. The argument behind it is that a self-driving Tesla stopped being a one-time sale and becomes a vehicle able to earn money around the clock, turning the fleet on the road into a network. Whether the technology will arrive on the timeline Tesla promises remains an open and heavily debated question. And the company has missed self-driving targets before, but the strategic logic is consistent. The cheaper each car is to build, and the more of them on the road, the more valuable a working autonomy system becomes. The same ambition reaches past cars entirely. Tesla has poured effort into a humanoid robot it calls Optimus, applying the artificial intelligence trained on driving and the manufacturing discipline honed on cars to a machine meant to perform physical labor. Musk has described it as potentially the company's most valuable product, though it remains early and unproven. The through line is that Tesla increasingly treats the car as a platform for software, sensors, and intelligence rather than as an end in itself. The competition then is no longer about building cars. Tesla is fighting across battery technology, software, manufacturing, artificial intelligence, real-world data, charging networks, energy storage, and global scale at the same time. And catching up in even one of those layers takes years. A rival might match the motor and still lack the cells. Match the cells and still lack the data. Match the data and still lack the factory that makes any of it pay. The advantage is not any one piece, but the way the pieces reinforce each other, so that progress in one quietly lowers the cost of progress in the next. Every one of them traces back to the same place. A cheaper motor means cheaper cars. Cheaper cars mean more cars. More cars mean more data. And more data means systems rivals would have to build from scratch. There's no quick fix for that. A competitor cannot buy its way out overnight or patent its way around it. It can only try to build something equivalent. While Tesla already has years of practice in the factories, ready to print the result, and by the time it arrives, the target has moved again. The drive unit was never really the announcement. It was the signal that the rules the industry agreed to play by no longer apply. The electric revolution is real, but it may not arrive as the level playing field many imagined. Instead of a dozen equals trading the lead, the shape forming is closer to one company compounding small advantages across many fronts at once, while the rest spend their effort catching up to where it stood 2 years ago. Whether that ends in dominance or simply a long lead, the contest has already moved past the showroom and into the factory and the data center. So is this the moment the electric vehicle war ends? Or is the competition far from finished? Could another company actually catch Tesla in the next 10 years? Or has the gap grown too wide to close? Drop your honest take in the comments, because the best debates always come from this community. And if you made it this far, hit the like button so more people see this breakdown, and subscribe if you have not already. There is a lot more coming on the companies and technologies, quietly reshaping the world, and you do not want to miss what comes next.